Okay, so today we're going to start chapter 10. Section 1 is going to be using properties of tangents. This chapter, or at least this lesson, is going to be filled with lots of wonderful vocabulary words that are going to be dealing with circles. Now, some of them you may have seen before, and then there will be other parts of the circle that you probably haven't seen before. So here is the definition of a circle, the center, and the radius. Circle is the set of all points in a plane that are equidistant from a given point in that plane. Okay, that given point is going to be called the center. A radius is going to be the segment whose endpoints are the center and any point on the circle. So it's basically from the center to the edge. Plural of radius is radii. So for example, if we draw a center, and then if I put a bunch of little points here, and all of them that are equidistant from that center, then if I were to connect my points, connect the dots, this creates the circle, and notice from the center to the edge, this is called the radius. No matter where you draw it, from the center to the edge, all of these radii should be the same distance. I know my circle's not exact here, but this radius, let's say it had a length of, this segment was 3, this segment would be 3, this segment would be 3. So from the center to any point on the edge of the circle is called the radius. Next, we've got a whole bunch more vocabulary here. We have a chord, and a chord is a segment whose endpoints are on a circle. A diameter, it's also a chord, but what's special about a diameter is it's got to contain the center of the circle. So it's going right through the middle. Okay, a secant is going to be a line. Notice the difference here. Okay, these were all segments before this. Now we're talking about a line, and that's going to intersect a circle in 2 points. And then a tangent is going to be a line in the plane of that circle that intersects the circle in exactly 1 point, called the point of tangency. So the radius, the chord, and the diameter are all segments. The secant and the tangent, their definitions state that they're a line. Now we're also going to see a secant segment and a secant tangent coming up, but for now, know that a secant will be a line. And I'm going to draw pictures of these. So when we have a chord, if I have my circle here, okay, so when you have a circle, we have the center point, a chord is going to be a segment whose endpoints are on the edges of the circle. They're on the circle. Okay, it could be anywhere as long as it goes from side to side. Doesn't have to go straight across. When it's a diameter, it's still a chord, but what's special about a diameter is it's going to go through the center. Now, when I usually would teach this, I would say, okay, if I make my diameter go up and down, think of it like this. If I outline this, this looks like a capital D. So when it goes through the center from side to side, this is the diameter.
The first one's a chord?
Yes. So the first one goes from edge to edge, but it doesn't have the center. Okay? The diameter is a chord, but it must go through the center. That's the difference. Okay? Then when you have a secant, the secant is going to pierce the circle. It's going to go through it. So for example, I could draw a secant here, and it's going to be a line that cuts through the circle. Okay, it's going to intersect the circle at 2 points. So it's hitting it here and here. That would be a secant. Then the tangent is going to be a line that intersects the circle in exactly 1 point. So it's like skimming the side of it. And it's going to hit it just here at 1 point. That point where it hits the circle is called the point of tangency. And the next slide has, I think, a better picture of everything. The tangent, here's the circle. The tangent is just going to be a line that just skims the side of it, and it's only going to touch the circle at 1 point. So it's skimming the side of it. It's not going to intersect it at 2 points like the secant does. Okay, so the next slide actually has a picture of everything here. Nice organized circle here. So we have the chord. Remember, the chord is a segment, and it goes from one edge of the circle to the other. We have the diameter. We don't have the center in here, but remember the diameter must go through the center. And again, it goes from edge to edge. Then the secant is a line. Notice the arrows on the end of it, and it's going to intersect the circle at 2 points. And then the tangent line is also going to hit the circle, but only at 1 point. That point where it hits the circle is called the point of tangency. Yes. Notice the secant is coming out of the circle. It's not stopping at the edges. Okay, next slide. Now we're going to practice this. We have an example. So it's telling us at the beginning that point O is the center of the circle. And it wants us to give all these vocab words a name to each one of these. Now, pay attention to which ones are lines and which ones are segments. Remember, this segment is just the straight bar on top. The line is indicated with the arrows on the end. So, I'm sorry?
It matters for each one, like each secant, tangent, it matters?
Yes. So we're going to name them differently based on what's on top. All right, so OM. Anybody know what OM is? OM is right here. What is that, Isabella?
Radius.
It's a radius. Good. Okay. MN. What is MN? Let's see. Let's highlight MN right here. What's the... Alex. It's a chord. Good. Notice it's got a segment on top of those letters. Okay, now we have line MN. So this makes a difference. Okay, it's a secant. Now technically this could keep going. So this is a secant because on top of the letters is a picture of a line here. So this is a secant. MQ. Okay, it's a diameter. Again, it's a chord, but when it's a diameter, we need to name that it's the diameter. So we want the most specific name here. So this is a diameter. Okay, ML. Bella.
A tangent.
All right. Now, this time we're going to say it's a tangent segment because notice the picture on top of ML is a segment. So we're going to say this is a tangent segment.
If it's not what the definition says, if it's like how a tangent has to be a line, if it's a segment but it's also a tangent, you have to put tangent segment, but you can't just
Correct.
put tangent.
Correct. Now, for the next one, same letters, but it's got the line on top. This one we could just name as a tangent. Okay, so when it's the letters of the tangent, but it's a segment picture on top, name it as a tangent segment. And then point M is what?
Point of tangency.
The point of tangency. There's also secant segments also. So for example, if MN, or it would be out of it, we would maybe call it MP or something, just know that if it's got a picture of a segment on top, write the word segment at the end when it's a tangent or a secant. More vocab. Now we're going to look at common internal versus common external tangent lines. So here, when you draw a segment connecting the centers of the circle, if the segment intersects the common tangent, then the tangent is internal. If it doesn't, then the tangent is external. So right here, I've got two tangent lines. I've got this one, and it's hitting both of my circles at this point of tangency. And then I also have this tangent line over here, and it's hitting at each of these points of tangency. So now what they're telling you to do to determine which one is an internal common tangent and which one's external, I'm going to draw in my centers, and I'm going to connect them. So I'm going to make a segment that will connect the centers. And this is off. Let me fix this up a little bit better. So I'm going to put a point. I'm going to connect my centers with a segment. Connect my centers with a segment. Notice the first picture to the left. Notice when I drew in that segment, that horizontal segment connecting the centers, notice that it does not intersect that tangent line. So this example would be a common external tangent. So this is a common, this line right here, common external tangent.
In a question on the test, they'll already give you the line, right? The tangent line.
They'll give you the tangent line, but not the connecting line. Okay, so this is a common external because it does not intersect that segment that connected the circles. Now for the next one, this is an example of a common internal tangent because it intersects that segment that connected the circles. So know the difference between common internal versus common external.
We're having a quiz on this, right?
You're having a quiz on this next week. It'll be the last grade of the quarter.
On 10-1 through what?
10-3. 10-1, 2, and 3. So we're going to actually spend 2 days on each one of these, practicing this. Again, just like we saw with the quadrilaterals, this is going to be a lot of vocabulary that you're going to need to keep track of. Do not wait until the night before the quiz to try to start cramming all this information in. So we are going to spend today and tomorrow on 10-1. Then we'll spend Wednesday and Thursday on 10-2.
We're splitting this up into 2 days.
2 days, just to make sure we get this. And then Friday and Monday will be 10-3. We will review next Tuesday, and then your last grade of the quarter will be on Wednesday, and it'll be a quiz. Next, we're going to learn about congruent and concentric circles. So congruent circles are circles that have congruent radii. Concentric circles are circles that lie in the same plane and have the same center. Can anybody think of like a real example, real life example of a concentric circle? A what? A target. Good, a bullseye. Okay? So like a bullseye or a target. That would be your, real life example of concentric circles. So a bullseye is an example of concentric circles. And you could have more than one. So like if you had another one, just know that they're going to have the same center. And each one will have a different radius length. Okay? However, the congruent circles, that's kind of hard to draw. But sort of like if you had one that was going this way and then maybe if you had another one that was cutting through it, going the other way. These share the same, they have congruent radii, but they're not going to be in the same plane. So one could be facing, you know, one way and then the other way. Like this way and then cutting it.
They have to have the same size?
Yes, because they have to have congruent. Well, no, they just have to have congruent radii. They're not going to be in the same plane.
Wait, which one's congruent?
This would be congruent, where they have congruent radii, and these are the concentric.
Why is that line like not a circle before?
I'm trying to sort of draw it three-dimensional. So it's sort of like, maybe I can draw it a little bit better, but maybe I'll come up front and I'll show you. So like one circle's this way.
Like this? Like, I get it. Like this, right?
Yeah, like they're inside, like it's slicing the circle and going the other way.
I'm confused.
Next slide. Coplanar circles that are tangent to the same line at the same point. So these are tangent circles, and they're all tangent to the same line at the same point. So notice this point of tangency is right here, and then this one's in between them. So both of these circles on both figures, they're in the same plane and they're tangent to the same line. So here's the tangent line, both of these. And then the point of tangency is the dark circle. Slide. Theorem 10.1. In a plane, a line is tangent to a circle if and only if, here we go again with the biconditional, and we could flip this, the line is perpendicular to a radius of the circle at the point of tangency. So this is a lot of words here. So this angle that's created right here, where the radius hits the tangent line, is a right angle. So if BC is tangent to circle A, then we know that AB is perpendicular to BC. We're going to be using this theorem a lot because we're going to be creating right triangles within this circle. Theorem 10.2. Tangent segments from a common external point are congruent. So this is sort of like the ice cream cone or the snow cone theorem. It sort of looks like it. So notice this theorem. If we have two tangent lines from the same point, then these segments AB is congruent to BC. Okay, now we're going to apply these. Okay, so we got two parts here. Part A, let's go ahead and label our given information. It's telling us that OR is 6 and OT is 8. Notice this is based on Theorem 10.1. We know that OR is perpendicular to OT. So I made a right angle here, so I have a right triangle. How can I find the length of RT? Good. Anybody else notice anything special about these numbers? Valentina? It's a triple. So if you've memorized the triples, then you don't have to do Pythagorean theorem. But I know most of you probably haven't memorized the common Pythagorean triples. It could be based off of the 3, 4, 5, and then just multiply everything by 2. So RT is going to be 10, but I'm going to go ahead and show you with Pythagorean theorem. A squared plus B squared equals C squared. So to find the length of RT, we're going to do A squared plus B squared equals C squared. 6 squared plus 8 squared equals our C squared. And our C squared is the RT. So 36 plus 64 equals c squared. Add them together, we would get 100. Square root it, and the length of RT is 10. But again, if you've memorized the triples, then just put a 10 there.
How do we know that O is a tangent?
Okay, so OTR is 45, OT is 4, and now again it wants us to find the length of RT. Anybody know what kind of triangle this is? Yes.
45, 45, 90.
Good. Anybody remember the relationship of the legs in the hypotenuse? Yes, Bella.
The 245 sides, the opposite one equals A, and then the one opposite from the 90 equals A square root 2.
Beautiful. So if you remembered that from the special right triangle chapter, then this is A already. A equals 4. So then RT is just going to be 4 radical 2. Now, if you didn't remember that, we can again do Pythagorean theorem. So let's go ahead and let's fill in. So if it's a 45 degree right triangle, again, I know both of my legs are 4. So I can do 4 squared, do it in black so we can see this a little better. 4 squared plus 4 squared is going to give us our c squared, which is our RT again. So I will do 16 plus 16 equals c squared. 32, square root of it equals c. I have to break down the radical. So I could factor this into 16 times 2. And square root of 16 is 4, radical 2. Same answer. It's a lot easier if you remember the relationship of the special right triangle. That's the easier way around this question. However, Pythagorean theorem works. You just have to simplify the radical. Example 3. Here it wants us to name a line tangent to circle P, but not circle O. Okay, can anybody name the line that's tangent to P, but not to O? Alexa.
Is it B?
Okay, we need to name a line with 2 letters.
Oh, CD.
CD.
Oh, because it can't be O.
Yeah. Tangent to P, but not to O. We can either call it OB or BO and put a picture of a line on top. Either way, good. Okay, can someone name the common external tangent to circle O and circle P? Juliana? CD, we need, let's see, name the common external tangent. Yes, CD, beautiful. Okay, so the common external tangent, remember a tangent is going to be a line that hits the circle only at one point. So notice CD is here. Remember, to find the internal and the external, you're going to draw.
Oh, extra, I see X.
So it wouldn't hit the connecting line. So it's out exterior.
The connecting line would be the middle diagonal.
Right, you would have to draw that in. So you would draw that in there. And because CD doesn't intersect that segment, then that's the external tangent. Okay, now name the common internal tangent to circle O and P. Bella. AE. Good. Notice when I drew in that black segment there, it's hitting the tangent, making it an internal common tangent. Last one. Example 4. Circle M and circle N are tangent at P. PR and SR are tangents to circle N. Circle N has a diameter of 16, the length of PQ is 3, and the length of RQ is 12. I'm going to go ahead and I'm going to fill in those numbers. So PQ is 3, RQ is 12. And the diameter is 16. So through here is 16. First thing it's asking for is to find the length of PM.
Why does it say P point PR? Or is that a period?
That's a period. Okay, so the first question is to find the length of PM. Notice if I were to draw in a radius here, notice if the diameter of the large circle is 16, then I know the radius of the large circle is going to be 8. So if I were to draw my radius here, it's going to cut through that one. And if I know that the radius of the small one, it'll be half of that diameter, I know the length of PM is 4.
But why is PM half of the radius?
Because when I drew in, remember, if this diameter here in red, see how it's 16? When I take half of that, that gives me the length of the radius.
Yeah, I get that. I just wasn't like the other half would be the PM score.
Because this is now the diameter, this 8, which is the radius of the big one, is now the diameter of the little one. And then to turn a diameter into a radius, divide it by 2. So now this radius of the little one is 4. All right, next it wants us to find the length of MQ. MQ. Exactly. So now we're going to draw in the segment MQ, and notice that the radius with the tangent line makes a right angle. And I already know 2 of the sides. I have the 3 and the 4 here. So I'm going to do Pythagorean triple or Pythagorean theorem, and really it's a common Pythagorean triple, which is going to be 5. But if you did 3 squared plus 4 squared equals the length of MQ, which I'll just say C, is 9 plus 16. And then add it, it's 25. And then square root it, and C is 5. So the length of MQ is 5. Now we need to find the length of PR. How can I find the length of PR? Jason?
You add PQ and QR.
Beautiful. And 3 plus 12 is? 15. All right. What about SR? Bella? Nope, there's a theorem we just learned about. Remember the 2 tangent lines that meet at a common point?
What is it? Also, it's also the cone theorem.
Yes, that ice cream cone theorem. Okay? Or the snow cone. So they're 15, they're congruent. So SR is also 15. NS.
8.
Good. Okay? The radius anywhere is going to be 8. Now, NR, we have to do Pythagorean theorem. So NR and then it's going to make the right angle here with the, yes. So I can do Pythagorean theorem, or it's a triple, either way. But 8 squared plus 15 squared equals C squared. 64 plus 225 equals C squared. And then we'll add this up and get 289. When I square root 289, my length is 17. So, big thing here is going to be knowing all of these vocabulary words for all the parts of the circles and knowing all of the theorems. The homework tonight, the practice A, is pretty easy. I started it. It's a lot of, naming stuff like on these examples, but also applications. So tonight's homework is practice A. Tomorrow we will go over the practice A answers, and then we're going to reinforce it tomorrow night, and your homework tomorrow night will be practice B. And then Tuesday we'll look at lesson 2. Any questions? Okay, so you can go ahead and start. You only have about 3 minutes. So you can go ahead and get started. If you have questions, let me know.